Hello, hope you are doing well. Today, I would like to talk about the freight transportation concept in the transportation and logistics systems. And to explain the freight transportation, I will present a very short version of one of my recent papers, and let's do it. So, today, I will talk about an advanced freight transportation system, which is an integrated hierarchical hub location and scheduled service network design. I am honored that I co-authored this paper with two great professors from Montreal. In this presentation, I will first talk about the introduction and background and the concepts for the freight transportation, for the hierarchical hub location, for the capacity planning, for the transportation planning, and the scheduled service network design. Then we will talk about the problem definition, the literature review, and a mixed integer program to formulate this problem. And finally, we talk about some conclusions about this presentation. So, what is a freight transportation system? The freight transportation facilitates the movement of demands from different origins to destinations where there are different transportation modes to do this movement. And the freight transportation contribute to a very high amount of GDP in every country. For example, it contributed around 19 trillion dollars for the United States in 2019. Uh, what is the hierarchical hub location? The hierarchical hub location, the hierarchical system is can be seen in different applications. For example, for the post office applications, we can see that the nodes are defined in a hierarchical way. We have the service nodes, which can be considered as the location of the customers or the location where we have consolidated the demands at the service nodes. And uh, then we transport the consolidated demands from service nodes to secondary hubs and primary hubs. In this concept, we consider some small terminals, such as, for example, in a real world. For example, the Quebec City terminal can be considered as a secondary hub in comparison with some larger terminals, such as the terminals in Montreal or Toronto or some other terminals, which are the primary hubs. So the movement of demands between these hubs draw draw network can be defined as a hierarchical hub location. So in this problem, we want to contribute the location of the secondary hubs and primary hubs that we have defined the service nodes in our system. We know what are the service nodes which are fixed, and to facilitate the movement of demands from different origins to destinations which are in different zones. For example, a service node can be a customer from a very short city in Quebec province. It is the origin, and the destination would be another city in Alberta. So these service nodes are located in very different zones. And to facilitate the movement between these zones where the customers are located, we provided the different secondary hubs and primary hubs where we can move and transport the shipments and demands between these hubs in our hierarchical system. We also talk about the capacity planning. So, in addition to the location of these hubs, we also want to talk about the capacity configurations. We know that each hub has a base capacity, but to cover the unforeseen demands and to be have a physical net to have a feasible network that we know that we can satisfy all the demands, we may need to provide some capacity configurations, some temporary capacity configurations to the hubs. These temporary capacity configurations are able to extend the capacity of the hubs to accommodate the transportation and to store the demands at these hubs. So another concept that we will talk about it in our problem definition is the capacity planning, where we consider temporary capacity configurations at hubs. Another concept is a transportation planning, where there are diverse transportation modes. We have rails, we have roads, we have sea, and we have airplanes. That these transportation modes can help us to transport the movements from different regions. For example, when we have a different transportation modes, we can consider that we can use the train for the movement of the shipments from Quebec City to Montreal, and then we can use airplanes for the movement of um, the from Montreal to another cities such as the city of such as the Vancouver, which is a very uh, great city, which is a big city. And then its destination is Victoria. And then we must use the ship to finally transport our shipment, our demand from Vancouver to the Victoria. So in this example, I use different transportation modes to move a demand from Quebec City to Victoria. So in this study, we assume different transportation modes for the movement of demands by trains, by airplanes, by ships to facilitate the movement. And what is the scheduled service network design? For example, we can consider the scheduled service network design uh, as the trains or any other public services. Each service has a planned route, where this route includes different stations, and this service must start from this first station to its last station. Assume that uh, this a train started its pass from station 1 on Monday. Then it goes to the second station on Tuesday. And for this uh, type of network, as we can see, there are different nodes that there are a set of conceptual connections which can be defined as arcs for the connection of these nodes as a network, and these services provide the the transportation or the movement from these nodes based on planned routes. Using the scheduled services where there are planned routes, we can satisfy time-dependent demands. Where the demands have a time window, we know we have a time window for its pickup from the origin, and there is also a time window to deliver it to the destination. So using the scheduled services, we know that how we can transport the shipments and demands from different nodes throughout the scheduled services. To define this problem more mathematically and define a concept, I would like to highlight that the proposed problem, which is an integrated hierarchical hub location and scheduled service network design, aims to determine the optimal location of the hubs for both secondary and primary hubs and their capacity configurations will help us that to provide an additional or an extra capacity for the hubs. We must also able to define or design the service selections where these services activate these nodes and connect these selected hubs through our network. And using this selection of the hubs, their capacity, and the selection of the services, we can define the demand itineraries, where these itineraries shows that each demand, how each demand starts its journey, its itinerary from its origin to its destinations. So to explain more details about this hierarchical hub location and scatter service design, I will talk about a physical network of time-dependent demands and the services in our system, and what are the strategic and tactical plannings related to the decisions made in this problem. So consider that we have three types of nodes where H belongs to capital H, define the primary hubs. There are secondary hubs where index I belongs to capital I, define the secondary hubs. There are a set of service nodes as the location or as the consolidated demands in our physical network, where we use J belongs to capital J as the service nodes. To define the hierarchical tiers, where we have three tiers, the bottom tier are the service nodes, the middle tier are the secondary hubs, and the top tier is the primary hubs, is defined by the index R belong to capital R. And we have transportation modes where there are different transportation modes for the movement between the tiers. As I said, for example, for the movement from Vancouver to the Victoria, we have only the sea and sea transportation mode, or the ships where they provide the movement from Vancouver to Victoria. For the movement from Quebec City to Montreal, we have trains, we have roads, and we have airplanes that provide the shipment for the this physical network. So there are different transportation modes for the movement. Based on these nodes, which are defined as service nodes, primary hubs, and secondary hubs, we can define a physical graph G where N defines the nodes and A defines the arcs. So each arc in our physical network defines a conceptual connection between two different nodes using a transportation mode. So it can be defined as this, where A is an arc and it includes N as its origin, N prime as its destination, and M is its transportation mode. So, as I said, we contribute to the location and capacity of the primary and secondary hubs. So, we consider that for to select the location to or to activate the location of both primary and secondary hubs, there is a fixed cost. And for the capacity planning, as I said, we consider that when we set up a hub, there is a base capacity, and we can add a capacity configuration can be added to the base capacity. So the parameter UHL defines that uh, which capacity configuration is defined for the node H, which is the hub H. So it defines the amount of capacity configuration for node H and using the configuration L. And of course, this capacity configuration has a fixed cost. So we consider that there is a fixed cost for this capacity configuration where GHL defines this cost. And the most important part of our this freight transportation system as the are the demands, where, as I said, each demand has an origin and a destination, where this origin and destinations are located from the set of service nodes, and each demand has a volume, and there is also a holding and handling cost for movement of this demand at the hubs. So the parameter C KH defines the unit cost for the handling and holding of demands at hubs. And the most importantly, there are some time characteristic parameters related to the demands. We know that each demand will be available uh, as a time where it is its release time that we can pick up the demand. And there is a preferred delivery time for this demand. So we can see that there is a preferred delivery time for this demand. And this delivery time is uh, between a time window where there is an earliest due date Also, there is a latest due date. So the preferred delivery time must be is with this range, and these demands are defined, and we expect that these demands are repeated regularly in our freight transportation system. So to supply these demands, we have a supply side. The supply side of this freight transportation system is the services. Where there are three types of the services. We have a set of services which can be defined as bottom tier services, where these services only assign a service node to a secondary hub. We have middle tier services where uh, such services provide an assignment between a secondary hub to a primary hub. And we have scheduled top tier services that such services provide the transportation between the primary hubs. So, to explain the scheduled services, we must know that each service has an origin and a destination, as it can be defined as it's the origin from its first transportation leg to uh, and a destination, which is the last station of the service from its last service leg. So, uh, and there is a service itinerary where defines the sequence of visits for the services, where we know that at which time each service starts its path from its origin to its destination, and through it, the service is able to visit the some middle uh, stations. So there is a fixed capacity for uh, for a service for to is based on this service this we can provide the that to meet the volume of the demands. So there's a fixed capacity, and this capacity is leg specific. It means that we know that what is the capacity of the service from from the first service leg, or what is the capacity of this service for its last service leg. So we have some definitions that there is a departure time for a service that shows that when this service it starts its journey from the origin, and there is also an arrival time to show that when a service arrives to the destinations. And the service duration is defined by deviation between the arrival time and departure time. From the economic view, we consider that there is a fixed cost for the selection of the services, and there is a variable cost or the unit cost to shows that how much we must pay for the movement of a demand by this service for each unit of the time. And there is also uh, we have to consider the time window, as we know that the time characteristics of the demands are known, we have defined a penalty cost. That the penalty cost for if we are not able to meet the desired time window of demands, has been added to the variable cost or the unit cost of the services. To calculate this penalty cost, it has been defined by a comparison between the arrival and departure times of the service and the time window of the demands when there is a release time, and also there is also a time for its delivery, and there is a time window for its delivery. So if the arrival time of service does not meet the delivery time for the demands, we have defined a penalty cost for this service. So from the definition of the services and the demands, we clearly know that if a demand will be assigned to a service, it will be uh, it will be delivered on time, or we have a penalty. This study contributes to both strategic and tactical planning. We can consider that the the demands are defined in a schedule length. The schedule length can be divided into equal time periods. And the for our planning horizon, which can be considered to both strategic and tactical planning, can be divided to the equal schedule length. For example, we can consider the schedule length as a month or a season, where the time periods are the day. So based on this, we can define that this study will contribute to the strategic planning, where the decisions related to the hub location and the service selections are related to the strategic planning. And we have tactical planning, where the decision related to the capacity configurations and the variable cost for the holding of the shipments and the selection of the services are related to the tactical planning. So this study contributes to both strategic and tactical planning. To define the literature, we can highlight that there is very, very few studies that consider the location and capacity configurations for SSND. So, although there are so many studies for the scheduled service network design, most of them focused on the tactical planning, where there are no study, or there are very few studies that contribute to the both tactical and strategic planning. So from this study, I can highlight that there are only two studies that consider the location of the hubs for the SSND, for the scheduled service network design, and this study also adds another new contribution to this area. To define a mixed integer program, we should highlight that all the parameters for the demands and the services are time dependent. So we need to use time and space networks to model the proposed problem. And so the proposed HHL-SSND model contributed to both strategic and tactical planning levels with the using a time space network. So what is a time space network? To define a time space network, we add the time periods to the definition of the physical graph. So there is a time-space graph where n as the nodes are defined by two dimensions: the location or the location and the time. So the set of n t belongs to the capital N shows that the status of location N at time D. So based on this definition, we can define the arcs as two types of arcs: the moving arcs and the holding arcs. The moving or the traveling arcs can be defined as the movement from uh, from a from a node to another node in two different times. Consider that from this example that with this for this arc, for this traveling arc, the origin is n, and the time that this arc is started is time t, and the destination for this arc is the node n prime, and the time that that this arc arrives to the destination is t prime, where t prime is bigger than t. So it can this can is the definition for a traveling arc. We are also have holding arc, where it shows the inventory status of a demand at the hubs. The holding arc it defines only based on the time difference between from the time where we know that there is a demand which is in in hop n at time t, and it must be kept at this uh, terminal or at this hop to time t plus 1. So based on this definition, it is the holding arcs. So another very conventional concept is that we can define the arcs originating from a node using this notation a plus nt, and for the arcs leading to a node we can define it as a minus nt. And to also explain that if a node belongs to an arc, we can use this notation. Based on this definition, we can consider a numerical example for this problem. Assume that there are three demands where they will be available at a time. For example, the first demand is available at time 1, where the second and the third demands are available at time 2. And each demand starts its this demand itinerary using the bottom tier services, and then middle tier services, and then the transportation through the top tier services, and then again uh, it uses the middle tier services, and finally it uses bottom tier services to arrive to the destination. So this are an example where it shows the status of each hubs in a time and space graph, where these hubs are maps are mapped by the time periods, and these arcs also show the services in the time and space graph. There are four variables to formulate this problem. The first variable, ZH, refers to the location variables of hops. The variable WHL refers to the capacity configuration for the secondary and primary hops. The variable Y refers to the selection of the services, and there is also a demand flow variable which shows that if amount of demand that has been assigned or has been traveling using an arc. So the objective function is defined as a total cost, where we consider the fixed cost for the selection of the secondary and primary hops, the fixed cost for the capacity configurations for the secondary and primary hops, the variable costs for the storing or holding the demands at hops, and also the fixed cost for the selection of the services and the variable costs related to the unit of transportation using the services. So it is also a demand flow for this variable. The first constraint shows that if we locate a hub, we must define its capacity configuration. That it means that if a hub is located, there is a possibility to define a capacity configurations which has been assigned to this hub. There is also two variables for linking the location variables and the selection of the services and linking the location variables with activation of the holding arcs. So for traveling arcs and the holding arcs, we define constraints 3 and 4 for activating them. Based on all the classical network design, there are 3 constraints that confirm that each demand must be picked up from its origin, and it must be delivered to its destination, and it must be picked completely through our physical network. So these constraints from 5 to 7 define the network flow in the proposed problem. There is also a capacity limitation for the services that we must meet the capacity of that is selected services for the demands must be able to meet the capacity for the related to the and the volume of the demands related to the services volumes of demands that contributed to the capacity of the services. And there is also a capacity limitation for the hubs. It means that if we store a demand at the hub, we must be able to satisfy the capacity limitation for the assigned demands to the hubs. So for both the capacity of the services and hubs, we must meet the capacity limitation regarding the volume of the demands and the capacity limit for the hub, for the services and hubs. And finally, there are decision variables where we have 3 types of binary variables, and also there is also an integer continuous variable for demand flow. So this is our mixed integer program. And due to our time limitation, I did not provide the details for the solution algorithm, and also the details for the numerical example. That is very comprehensive, and it may be far from your time. So I invite you to search the paper and see more details about it, or you can contact me by emails to have more details about how we can solve this model and what are the numerical results for this paper. So uh, this paper provided a new integrated multi-tier hierarchical hub location and schedule service network design as an advanced freight transportation system where we contribute to both strategic and tactical planning. So, to define and to provide the continuations of this research, there are many ideas where we can consider the uncertainty, we can uh, consider different interesting ideas about using the artificial intelligence and machine learning for the solution method, and consider other consider the sustainability criteria for this freight transportation system to move it through the sustainable transportation. Uh, Thank you so much. I hope that this presentation helps you to have a better understanding about the freight transportation and the hub location and the schedule service of the design. Thank you so much and have a great day.